Okay, this is going to be the video for section 4.3 for differential equations, which is solving homogeneous linear differential equations with constant coefficients. So we'll have our first higher order method where we don't have to be given a solution. We can come up with a solution from scratch. All right, so for second order linear differential equations, we now have a method where if we happen to know one solution, we can find the second solution, right? But for linear homogeneous equations of any order, if the coefficients happen to all be constants, then we can use this method here to solve, meaning something like this. If we have something which is, say, a third order differential equation where we have y cubed, third derivative of y, second derivative of y, first derivative of y, y, this is a linear differential equation because all of these coefficients here are all either constants or they are functions which only involve x. But if we can go even further and say they're specifically all constants, so there's all constants and it's homogeneous, which means the right-hand side is 0, then we can use this method here. Okay, so the method here consists of representing the differential equation with a corresponding algebra equation, and then finding the solutions for the zeros of that algebra equation, and then using those results in one of three different standard forms. Okay, the derivation of why this works is pretty interesting, but it's pretty involved, so I'm not going to include it here. But if you're interested in that, there's a separate PDF with the derivation for section 4.3 that you're welcome to look at if you want to know the theory behind why this works. We're going to treat it as a procedure, though. So the way it works is this. We have a given dE, we find what's called its auxiliary equation. So the auxiliary equation is an algebra equation that mirrors stuff about the original differential equation. So if we have an equation of the form, we'll just do a second order one for illustration, but this could be done with any order. So let's say we had a second order one. So we have a second derivative, potentially a first derivative term and a no derivative term. And let's say the constants are called a, b, and c, and this is 0 over here because this only works for homogeneous equations. Then what we do is, for this term that has a second derivative, we replace the y double prime with just m squared. And we replace the y prime with just m, and we replace the just y with no derivative with no m at all. So basically, the power of the m determines the order of the derivative. So if it's a second derivative, it's m squared. First derivative, it's m. If there's no derivative, it's just the constant itself. And each of these are multiplied by their coefficient constants. Then what we do is solve the auxiliary equation by factoring if we can, or we resort to the quadratic formula if we need to, if it doesn't factor. Or if we have higher order terms, we can try things by like factoring by grouping, or we can even try guessing a 0 and using synthetic division to check and continue factoring. So any way you can think of to factor polynomials, right? And that will result in some combination of m values, these m's for the auxiliary equation, which are zeros, which are also sometimes called roots of the auxiliary equation. And they will occur, these m values will occur in one of three possible ways or some combination of these. You could have m's which are single or what we call distinct real roots. And so what happens is for each of those, you add a solution, you add to the solution a term of the form a constant times e to that mx. If you have a real root, but it's repeated, like you end up with, say, m cubed and then something here. So there's a multiplicity of 3 for this value of 0, let's say, or let's say you had m minus 1 squared. There's a multiplicity of 2 with the m value 1. Then what you do is for the first copy, you include a term like part A, you put a constant times e to mx. But then for each additional one, you put a constant, but you add an additional x in here. So for example, if your factored auxiliary equation ended up including an m minus 2 cubed, that's a multiplicity of 3, 0, where m is 2, then you're going to put a term in your solution that's a constant times e to the 2x, but the second one will be a constant times x times e to the 2x. And the third one that you add for the third multiplicity will be constant times x squared times e to the 2x. So you just tack on another x for each additional multiplicity that you have. And then sometimes you'll have values here where the only solutions are complex numbers because you had to resort to the quadratic formula and you got a square root of a negative. That's okay. You can have a complex root here. We write that m as a complex number where the real part is called alpha plus I times beta. Beta is the complex part. And then it turns out that for each pair, you add the following. You say, instead of including two separate roots with this, you include this for each pair. You say a constant times e to the real part of the root x times cosine of the imaginary part x, then plus another term with a different constant times e to the alpha x times sine of the imaginary part x. Okay, so we'll just do examples of each of these so you can see. Like I said, the derivation of why this works is actually quite interesting. I've included that in a separate function, but it's challenging enough just to use the procedure, so we're focusing on the procedure right now. But I would encourage you to read the PDF if you like to see why this kind of semi-magical thing works. It's really kind of neat. All right, so let's say we wanted to find the general solution for this homogeneous equation, right? We've got a second order equation here. So what I'm going to do is first verify that I can do this. It's linear. All of the coefficients here, 1, -36, are constants. There's no variables. And then the right-hand side is 0. It's homogeneous. So I can do this procedure. And that means I'm going to copy this equation, but make the auxiliary equation. The auxiliary equation is 1 times m squared minus 36 times, and there's no derivative here, so there's no m. And then I just do whatever I need to do to solve this, right? So I could, for example, factor this into m plus 6, m minus 6, and say, therefore, I know that m is either equal to -6 or m is equal to +6. Okay, if I get a distinct real number like this, then to my solution, I'm going to add a term that says a constant times e to that number x. And then I'm going to add another term for this other distinct root with a different constant, e to the +6x. And that's it. That's the solution. So really straightforward. Yeah, there's a lot of theory behind why this works, which is interesting. But in application, it can be very straightforward, much faster than some of the other procedures we have. Let's do another example. Find the general solution for this. Okay, it's linear, it's homogeneous. We have a 0 over here. All the coefficients are constants, so we're good to go. We'll make the auxiliary equation, which in this case is m squared minus 10m plus 25, no derivative here, equals 0. So I'll try to solve this. This one actually is solved by, we can factor this. It factors into m minus 5 times m minus 5, which really means we have a multiplicity of 2 root here, right? We have m equals 5 with a multiplicity of 2. Okay, when that happens, what we do is the solution is going to be a constant times e to the 5x, just like we would if it was a distinct root. But to get the second root, we'll just add on another constant times x times e to the 5x. And that's the solution. Okay. These are general solutions because we haven't used initial values to establish the constants, and that's okay. Okay, let's look at another example. This one is a second order differential equation again. Let's see, it's linear, it's homogeneous. We have constant terms, we're good to go. So let's make an auxiliary equation, 2m squared minus 3m plus 4 equals 0. Okay, you can try to factor this, but there's no factorization that works involving integers. So then we would resort to the quadratic formula and say, all right, m is going to be negative b plus or minus the square root of b squared minus 4ac over 2a. So we end up getting 3 plus or minus the square root of, that turns out to be negative 23 over 4. So since we're taking the square root of a negative, this is going to involve imaginary numbers here. So that this is going to end up being 3/4. 3/4. Let me do it down here. My tablet's acting up a little bit. Plus or minus, this is going to be the square root of 23i over 4. So you can think of it as the square root of 23 over 4, and then when I factor out the square root of -1, that becomes I. So this is my alpha, and this is my beta. And so the pattern is, when you have this, we have a complex conjugate pair, right? We have 3/4 plus this value I and 3/4 minus this value. So the pattern says that the solution will be some constant times e to the alpha part x times cosine of the beta part, the complex part, x, plus another term, which is the same to begin with, just a different constant, 3/4. Oh, there's an x here. So not alpha. Sorry, let me back up. That is alpha, not we don't write alpha. It's y equals a constant times e to the 3/4 x, the variable, and then times cosine of the beta constant, x, plus another term, which has the same real part, but we use sine. So they occur as sine-cosine pairs like this when we have a complex conjugate pair. Right, so this would be the solution when we have complex roots. And they'll always occur in complex conjugate pairs, so you always end up with this. Okay, let's get a couple more examples here. Find the general solution for this. So linear, homogeneous, constant coefficients. We have m squared plus 9 equals 0. Okay, so I could go ahead and just solve this. We can't really factor directly, but what if we did this? M squared is therefore equal to -9, so m is plus or minus the square root of -9, which is plus or minus 3i. So this is a complex number. It's just that alpha happens to be 0. So my alpha plus or minus beta I, alpha is 0. It's just purely complex. That's okay. We use the same pattern. We just say y equals c1 e to the 0x cosine of 3x, because the beta is 3, plus c2 e to the 0x sine 3x. But since e to the 0 is 1, we would just write this as c1. This is just a 1 here, so it's just c1 cosine of 3x plus c2 sine of 3x. So this is the solution when we have a purely imaginary root from the auxiliary equation. Okay. And then I just have one other example for you here that involves synthetic division. So sometimes this is important when you do this with higher order. I'm going to show you actually two ways to do this. One way is we can try factoring by grouping. So let me, here's my auxiliary equation, m cubed plus 3m squared minus 4m minus 12 equals 0. So how can I factor this and find its zeros? One way is you might luck out and factoring by grouping might work, which means we group some terms together in pairs like this. And then I'm going to put this as plus and then negative 4m minus 12. Okay. And then I'm going to try to factor the common elements out of each. So if I pulled an m squared out here, I would get m plus 3 left. And if I pulled a negative 4 here, I would also get m plus 3. So this is one of the cases where factoring by grouping worked because I got the same thing here, which means I can now factor that out, m plus 3, which would give me m squared minus 4 left. And then this is a difference of squares, so this could further factor into m plus 3 times m minus 2 times m plus 2. So it looks like I have three distinct m real values. I have m is negative 3, m is positive 2, and m is negative 2. So that means my solution is going to be y is some constant times e to the negative 3x plus a different constant times e to the 2x plus a third constant times e to the negative 2x. This is the solution. So that one we were lucky. We were able to do it by factoring by grouping. So this is by grouping. That doesn't always work though. So sometimes you do this factoring and then these two things are not the same, which means you can't keep going. So here's another method we could use. We can use synthetic division. But to do synthetic division, we have to guess one root right first, okay? Or make a guess at what might be a root. So if you think way back to Honors Algebra 2 probably is where they might have talked about this, and they may not even have talked about it then. We used to teach it years and years ago, but it may have been removed from the curriculum. There's an idea called the rational zeros test, which means that if you look at the coefficient at the end here and you write out all of the factors of that number, 1, 2, 3, 4, 6, and 12, and then you take the first coefficient, 1, and you write out all of its factors, then any ratio like 1 divided by 1, 2 divided by 1. So basically all these numbers are possible places where zeros might happen. And if there are any rational zeros, they always happen at those ratios. So what we could do is guess one of these and just try it. So let's pick one. Let's just try 1 over 1. Let's try 1. Now the way we try it is we do synthetic division. So the way synthetic division works is we take the number we're trying and we put it here. And then we put a bracket, and then we put the coefficients only, putting zeros as placeholders for anything that's missing. So I have 1 for the m cubed term, 3, m squared. The m term is -4, and then the no m term is -12. And I prime the pump by copying this 1 down here. And then what you do is you take the outside numbers and multiply them and write the result here. So 1 times 1 is 1. And then you add as you go down this way. So 3 plus 1 is 4. And then you take now 1 times 4 and write that here. And 4 and -4 add to 0. 1 times 0 is 0. And then this plus this is -12. And you've got a new polynomial. This polynomial here is x squared, or I'll use m. It's m squared plus 4m plus 0. But we have a remainder here. So plus -12 over x minus 1, right? So if you take this polynomial and you divide it by x minus 1, you get a result, but it has a remainder. So this didn't work, because if you're factoring, you're trying to divide out so that you have no remainder left over. It just divides evenly. So you just have to guess numbers and try them with synthetic division. So let's jump up here to +2. We could also use the negatives, by the way. It's positive or negative. But let's jump up to try 2. I'll do that over here. If we try 2, and we do that synthetic division procedure from way long ago in the past, 1 times 2 is 2. 2 plus 3 is 5. 2 times 5 is 10. 10 plus -4 is 6. 2 times 6 is 12. Remainder is 0. Aha, this worked. That means that if you take this and you divide it by x minus 2, in fact, let me write that, or m minus 2. If you take m cubed plus 3m squared minus 4m minus 12, and you divide it by this m minus 2, you get this polynomial here, which is m squared plus 5m plus 6, and there's no remainder. So that divided out. That means this is a factor. So that means that we can write this polynomial as m minus 2 times m squared plus 5m plus 6. And then if we're lucky, this will factor. So we've got m minus 2. And this would be m, they're both plus, so plus 2 and plus 3, right? M plus 2 and m plus 3 gives me, yep, that works. So now we get to the same spot we were here. We get the same numbers and we get the same solution. So if factoring by grouping doesn't work, sometimes synthetic division techniques will work. You guess a root, you try synthetic division to see if the remainder is 0, and if it is, you reduce the order of the equation by factoring one factor out. And you can keep doing this until you finally get something that you can factor with trinomial factoring. Okay, that is the last example. So just various ways to factor, but man, this can be a really fast procedure. You just have to kind of memorize the 3 forms, right? You either are using, you have a complex root where you have this form. You have multiplicity where you just keep adding on x's if you have to add more multiplicities. And if you have distinct roots, you just copy them in the form of e to that number times x with a constant. All right, that's it for this video.